I'll talk about my current research, which is based on slow pyrolysis of biomass to focus on the char and to use it to remove contaminants from water. This is my work at Aston University in the UK. And I'm part of the Green Carbon project as well as like Christian is. So I'll give a brief introduction to the research, why I'm doing it, what are the objectives, describe the methods I'm using, show you some results from removing a dye from water, how it relates to the char quality and the slow pyrolysis conditions, and then we can have some discussion around what I found. So since I'm looking at decontaminating water, adsorption is a very effective technique and it's very popular in wastewater treatment. The main adsorbent used in the world is activated carbon. You may be familiar with it. Its demand is increasing every year because we're always polluting air and water, of course, and governments are implementing more strict legislation around contaminants in water. So there is a need to clean water and air. Activated carbon can be used, as I said, for air decontamination and water. And it can be made in different forms, in powder, in pellets, extruded form, as you can see in the picture. It's the particles of the activated carbon. So it's a carbonaceous material. And the important feature is that it has high porosity and different types of pores, so smaller or larger pores. And this gives the material high surface area, so it can have lots of, let's say, sites for the contaminant to adsorb to. So this is achieved through a process called activation, which can be said to be similar to pyrolysis, but it uses activating agents such as steam or CO2, or some acids like phosphoric acid or bases such as hydroxides. And it applies high temperature, usually above 600 degrees, or even higher. It can also be lower depending on the activating agent. And it also does the process for a relatively long time, usually above 1 hour. And the feedstocks are usually, the most popular is coal, or coconut shells is also a popular feedstock for activated carbon. It's often done industrially in 2 steps, if it's physical activation with steam or CO2. So first you carbonize the material and then you activate it. But it can also be done in 1 step, especially in the chemical activation type. So there's lots of research around this because this process is resource and time consuming. If you're using acids, strong acids or bases, you're creating waste streams which are harmful. You're wasting, not wasting, but using lots of energy for a long time as well. And there are sustainability issues regarding using coal, which is fossil fuel, and also coconut shells, which are not available everywhere, of course. So there has been recently plenty of research around developing novel materials for adsorption and replacing activated carbon. So in my work, the main part was doing slow pyrolysis of wheat straw in a screw reactor. It's a lab scale reactor studying the effect of temperature, residence time, and carrier gas, for example, on the product yields and the quality with a focus on the char products. And then I decided to apply the chars to decontaminate water. I chose organic contaminants instead of inorganic, such as heavy metals. And then I chose a dye as a model compound, which is standard. It's normal that researchers do this. And then I looked at optimizing the production process to get char quality, improved char quality for this decontamination through modifying the process itself, trying to incorporate it with activation strategies, physical with steam and CO2, or chemical with KOH. So onto the methods, you can see here a picture of the feedstock used. As received form, it came as broken pellets. And the slow pyrolysis conditions I used were 3 different temperatures and 3 solid residence times. This was limited by the screw speed. So I had a maximum of 10 minutes residence time of the material inside the reactor. And then the first activation procedure, let's say, I tried to do was physical activation with steam, but instead of doing this by steam injection, which is the traditional activation procedure, I artificially raised the feedstock moisture content by soaking it with water, which ends up looking like this. So you soak the original feedstock in water, it absorbs most of the water, and it crumbles, the materials crumble up. So I got moisture contents of around 50 and 75%. And the other method of physical activation was using CO2 now as injection with as carrier gas. And this physical activation and slow pyrolysis is done in one step. Instead of doing pyrolysis first and then activation, I'm doing it in one step. So seeing how the CO2 and the evolved steam from the material interacts with the material itself to see what's the consequences of that. And then regarding chemical activation, I made KOH solutions with different concentrations. And again, I soaked the feedstock with the KOH solution and tried to incorporate the KOH into the material and then pyrolyze it, doing it chemical activation and slow pyrolysis in one step. And for these, the process modifications I chose both the lowest and the highest temperatures I used before to see what would be the effect of this. Chemical activation can be done at lower temperatures, according to research. Physical is usually done at least at 600, but I wanted to evaluate what was the effect of these two temperatures, and then I chose the maximum residence time possible to ensure that the contact time between, especially with the CO2 and the steam, that the contact time was as much as possible, although industrially it's around 1 hour or can be even more than that. And then the adsorption procedure. So I chose methylene blue, which is the most commonly used dye to study the adsorption with chars and other materials in water. It has alkaline character. It looks like a very dark blue in solution, and then as you remove the dye, you clear the water. Hopefully that's what you want. So I had the char ground to a certain and sieved to a particle size, and I mixed with the methylene blue solution, a certain amount of each for 3 hours, 50 Celsius, and then centrifuge to separate the solids from the liquid, and then measure the final concentration with UV visible spectroscopy. So these are the first results of the adsorption performances. So these are the three temperatures I did slow pyrolysis at, and these are the 3 columns are 3 different residence times, so 3, 6, 10, 3, 6, 10. And I also compared with a commercial activated carbon. This serves as the standard control tests, let's say. So it removes, because that's its purpose, it removed 99% or more of the dye, which was expected. So what I found was that the lower temperature chars were outperforming the higher temperature chars, which is interesting because you could expect that as you increase temperature, you increase porosity and surface area. But this did not translate into the adsorption performance, which is interesting. So when it achieved comparable removal percentages to activated carbon, which is good. And seems there's a trend, increasing trend with solid residence time, but only for the lowest temperature, and then a decreasing trend for the other 2 temperatures. And for the conditions I used, I got more or less 38 milligrams of dye per gram of adsorbent used, which this is the adsorption capacity for these conditions. So then I started testing the other chars I produced, the chars from the experiments with elevated feedstock moisture content. I saw the same trend with temperature. So the lowest temperature achieved the highest removal percentages, and the other ones were not as close to that one. But I saw no difference between the 2 different feedstock moisture contents. But still, the removal was was good with these chars. And then with the CO2 atmosphere, for the lowest temperature, the CO2 outperformed the chars from using nitrogen as carrier gas or from not using carrier gas at all, which is possible in the screw reactor. So this is good. There was some effect, it seems, from using CO2 on the char quality and thus the adsorption performance. But at the highest temperature, there was no particular difference between using CO2 or not. And then using the chars from the KOH experiments, that's when I got the highest removal percentage. So that's even more comparable with the activated carbon. But that occurred for the lowest concentration tested. And I got the opposite effect for the highest concentration. So there was a drop in adsorption performance, which is interesting. We'll try to explain this ahead. And another interesting thing that I found was that the adsorption performance increased significantly for the highest concentration, but at the highest temperature, which is something interesting as well from these results. So other tests I performed was using a different adsorbent mass, so how much char or activated carbon I would use for the test. So the standard was 25, but I also tried with 10. So what I found with this was that when you use activated carbon, the adsorption performance was reduced considerably when you were using lower amount of activated carbon. And I could get very good removals even with lower amount of chars for the slow pyrolysis char on its own, and from the char from the elevated feedstock moisture experiments. And also this one is, let's say, it's comparable to the activated carbon. And then looking at the adsorption capacity, which each two values belongs to the columns here. So I found that the adsorption capacity could be increased more than twofold for some of the chars, for these chars in particular, which is very good. So you use less char to absorb the same amount of dye, which is brings benefits economically. So I also looked at how the adsorption evolved with time. You do that it's like a kinetics test. You can fit different kinetic models. But just looking at the adsorption percentage with time, the activated carbon, I think you can see it, it's behind here. It's very fast, which is what you want with an activated carbon. You want it to remove a lot of the contaminant and to do it fast. That happened. But I also achieved very good removals with one of the chars here, the one from elevated feedstock moisture content, and also very good with the slow pyrolysis char on its own. And then these are lower, but still okay, and they are increasing. The total test time was 3 hours, so 180 minutes, and this is relatively short time for adsorption. So it's good that I got comparable speeds, let's say, rates of adsorption. And then fitting kinetic models to this data, I found that the best fit was pseudo second order kinetics, which usually suggests chemisorption occurring. So a two-step process of accumulation of the contaminant and then adsorption with more, let's say, more energy than physisorption, which is more lower energy adsorption. So another thing I did to try to explain what was happening was I tried an acidic dye instead of an alkaline dye, which was methylene blue. So I tried methyl orange. And again, the activated carbon achieved very high performances. All of the acidic dye was removed. And then with the chars from slow pyrolysis, I saw that the performances were not close to what I achieved with methylene blue. And then testing other chars, this was the maximum removal I got with the chars, with all the chars I produced, so 38%, which is not very good. But this was achieved at the highest temperature tested, which is interesting, and that's one of the elevated feedstock moisture content experiments. So that's interesting. And from the other chars as well, I didn't get any improvements from the 23%. That was the maximum for 400. I even got no dye removed for this char. And again, this was the maximum achieved. So this is suggesting that it's the chemical functions present in the lower temperature chars that are causing the high absorption of the methylene blue. So if it's an alkaline dye, it would become attracted to acidic functionalities on the lower temperature char, which makes sense because the lower temperature chars will have more oxygen elements on the surface and hydrogen, so more acidic elements to connect with the dye. Excuse me. So then looking at the char properties and trying to correlate with what was happening in the absorption, I looked at the porosimetry, of course, we're using nitrogen, and this is what the usual. I'm not putting all the isotherms here, but this is they all more or less look like this one. So the volume absorbed is very low, and there's some hysteresis between adsorbed and desorption that was happening variably between the chars, but it's usually occurred. And the surface areas are very low compared with the activated carbon, which is hundreds. Commercially, you can find activated carbons with thousands of square meter per gram surface area, and the chars were all very low in surface area. So this is suggesting that the material is non-porous, or that it can have very narrow micropores, so the nitrogen cannot diffuse easily into those pores, especially at the lower temperature of 77 Kelvin. So something you do to try to evaluate this is doing CO2 porosimetry instead. So that's done at 0 Kelvin, not 0 Kelvin, not 0 Kelvin, 0 Celsius, sorry. And then the diffusion of CO2 is easier, so it can diffuse into the narrow micropores. And indeed, I saw an increase in surface area. So the higher temperature chars achieved 100 square meter per gram. This is micropore surface area. And I saw an increase with temperature. Unfortunately, I couldn't do it for all of the chars, and that would be good to do, but I don't have that information now. So then I looked as well at approximate analysis, the volatile matter, fixed carbon content. For the chars from the elevated feedstock moisture content, I saw that those had a higher volatile matter contents. And this was connected to, since you have a higher moisture, then it takes longer to evaporate all the moisture. So you're reducing the time available for carbonizing the material in the reactor. And then I also saw carbon content decreased with the elevated moisture content and the oxygen increasing, which was related to the same reason before. However, this was only found for the lower temperature chars, which is interesting. So then I looked at the infrared spectra for the chars. The top three are the 600-degree ones, and the lower three are the 400-degree ones. So there were no significant differences between the three 600-degree chars, but there were differences for the 400-degree ones. So particularly in these areas, so the CC double bonds, the carbon-hydrogen bonds, and the carbon-oxygen bonds suffered some increase for the elevated moisture content, which was correlated with the decrease in carbon content and increase in oxygen and volatile matter. And then looking at the CO2 experiments, I saw that overall, using carrier gas, either nitrogen or CO2, the volatile matter is decreased, which is related to you're reducing the contact time between the vapors and the chars, so you can sweep out some molecules, even some tars, from the reactor, so they won't stay in the char. That reduces the volatile matter. And I saw that CO2 had a stronger effect than nitrogen. So there is something occurring with the CO2 comparing with the nitrogen. So there's a stronger decrease in volatile matter and larger increase in fixed carbon. Looking at the elemental distribution, at 400 degrees, only the CO2 had an effect in reducing the carbon, increasing the oxygen contents. And at 600, there was a slight increase with the nitrogen for the carbon contents, but the opposite for the CO2. So the same effect with the CO2 for both temperatures, so decrease in carbon and increase in oxygen. And this can be related to the absorption. So the CO2 char at 600 was found to have good absorption performances compared with using nitrogen or no carrier gas. So this can be potentially related to the higher oxygen contents in the char. So higher, greater chemical functionalities in the char to have more affinity with the dye. So then I look at the KOH chars from the KOH experiments. I saw that the KOH chars had higher volatile matter content and lower fixed carbon. The effect was higher for the higher concentration KOH, which was normal. And then the ash contents, of course, increased significantly for the highest concentration of KOH for both temperatures, because you're adding KOH, you're adding inorganics to the char, so you'll have more inorganics or higher ash contents. That was expected. And as maybe you remember from before, the absorption performance with the highest concentration of KOH for 400 degrees was lower than the other one. This was the best one. And maybe this could be related to the higher ash content. So the higher the inorganics can be covering up the surface and not allowing the chemical functionalities to interact with the dye, or they're even filling up the pores, the narrow micropores that can be occurring. As for the elemental distribution, there was an increase of carbon for the highest concentration of KOH for 400 degrees, but the decrease for 600 degrees. So opposite effects between 400 and 600 degrees, which is interesting. So maybe different mechanisms occurring here, because the KOH, there can be some melting occurring at one temperature or the other. So that's maybe why. And relating this to the absorption, so the 400 degree char with the lowest concentration was the best performing char, and maybe this is probably related to the higher oxygen proportions again. So again, the functionalities on the surface are more available to interact with the dye, and it was not hampered by the ash content, which is not significantly changed compared with no KOH. So this is interesting. I also looked at the pH and the infrared spectra of these chars. I found that the CO2 ones were slightly more acidic than the other ones, which can again be related to higher oxygen contents and also to the affinity of the CO2 chars to the alkaline dye, and also some changes in the surface chemistry, especially at 600 degrees. Then the KOH, from the KOH experiments, the chars were significantly more alkaline, which was expected because I used the hydroxide, incorporating it into the material. And then also I saw surface chemistry changes, the carbon-carbon double bonds suggesting aromaticity increasing, but also some oxygen bonds increasing, which was found for the elemental analysis as well. And then the higher KOH concentration at lower temperature, I found connections to oxygen decreasing, which again corroborates what was found in the elemental analysis, which saw oxygen decreasing for these conditions. So summarizing what was found, the Wheatstraw char was effective, had comparable performances to the commercial activated carbon at removing this organic dye from solution, the methylene blue, especially the lower temperature one, the 400 degree one, and that the surface chemical functionalities play a more important role than porosity, at least for the chars, because the activated carbon had very high surface area, and it probably plays an important role there. And also that activation was not promoted by the modifications. I did at least, well, if porosity was not increased, at least the nitrogen surface area with BET was not significantly changed. Maybe there's more narrow micropores, but it seems that it's the chemical functionalities, the surface chemistry changes that are contributing to the changes and increases in adsorption performance for some cases. So specifically for each of the modifications I did, so there was a slight enhancement of the adsorption for the chars produced at 400 from feedstock with elevated moisture content due to more functional groups and acidity, and no significant change for 600 degrees. Same goes for CO2 as carrier gas. And then the KOH chars, there was better adsorption for the lower concentration of KOH at the lower char temperature, again due to functional groups and oxygen contributions, but opposite effect with the higher KOH concentration, which was likely to be due to filling of the pores and the surface by inorganic materials. So in terms of what else can be done regarding this, what's important to look at is applying these chars for not just for dye decontamination, water decontamination from dyes, but to real wastewater from pharmaceuticals, and even having more than one contaminant in water. That's important for research. Applying it in real applications such as stormwater remediation, which I've seen in some countries are doing now, which is very good. And also what to do with the adsorbent after you use the adsorbent. So would you regenerate it through a thermal process? Would you apply HTC or try to desorb it with some solvent? Or could you even apply it to soil? Maybe not with the dye in the char, because maybe you end up with blue soil or blue potatoes. But maybe if you're adsorbing, for example, phosphorus, if you apply it to the soil after, maybe it can have a positive effect. So that's a cascaded use of the char. And that's really an interesting way to go with char. And also something interesting is evaluating the pH contents of the chars and see if things can leach from the char into the water, especially for the lower temperature chars, which are less stable than the higher temperature chars. So that's something interesting to do. And for the process itself is looking at how economically how the different modifications compare to each other, if it's worth it to soak the material or use CO2 as carrier gas. Trying different feedstocks is very important as well. So the results I obtained are for the feedstock I used. They probably all get something different with different feedstocks. That's very normal. It depends greatly on the feedstock. And then when you have a commercial process or you're trying to scale up, you need to figure out what to do with the byproducts. So you have either vapors if you don't condense into liquids, or you have liquid product and gas products. So you need to figure out what to do if you want to produce heat, if you want to separate some chemicals from the liquids, but you need to know what to do to have a economically viable process. So that's my presentation. Thank you for your attention. Sorry if it went a bit over time. If you have any questions, feel free to ask. Thank you.
Thank you, Filipe. Indeed, you got some questions. So I think I have to ask for short answers because there are quite some questions.
Good.
Have you measured the process distribution of the biochars?
Yes, I didn't look at. I didn't show that here. And also with the nitrogen, I didn't do it for the CO2 ones, but with the nitrogen ones, it's not very applicable because they're not measuring the micropore area very well, as you can from the surface areas. But that's something interesting to do with the CO2 isotherms.
Then David asked, would char be deployed like a reverse osmosis sort of bladder for filtration? The char be reactivated?
So I think that's how some companies or some research institutes are doing it for stormwater or riverbed decontamination. I guess it can be something similar to this, reverse osmosis, or sometimes you do it in a continuous column, but I did in batch tests. Reactivation, I didn't do any reactivation or regeneration, but you can do different thermal processes or HTC or desorption with solvents.
Sorry, I was asking, how long did your batch studies run for to ensure thermodynamic equilibrium, given that in the slide number 10, the absorption is still increasing after 5 minutes?
Yeah, so the absorption tests were for 3 hours maximum. So that's when I present the maximum absorption, that's the value at 3 hours.
Have you compared obtained isotherms with other studies? Are you sure that the biomass is converted at the set temperature? So if you actually fully carbonate your material at 400 degrees or 600?
So looking, I didn't show here the element, the proximate and ultimate analysis for the slow pyrolysis chars. But if you compare them, especially between different solid residence times, there are some differences, but it can be said that carbonization is complete. Even, well, visually, if you break down the particles, they're all uniformly black, then maybe that's not the best approach for carbonization, but it's if you're torrefying, so if we did lower temperature, you would see brown bits on the biomass from not carbonized material. So I think the biomass reached that final temperature, yes.
I'm skipping some questions that are a little bit repeating each other. Did you measure the surface area of the feedstock?
No, I did not. Don't think, no.
Did you test the absorption capacity of the feedstock? Because that I think that could be interesting.
Yeah, I didn't test the surface area, but I did test it in the absorption tests. So I did the same procedure, and it was interesting because you can also achieve high removal rates with the feedstock. And I've seen that there's research on using biomass itself for removal of contaminants, but something you get is the biomass is not stable, so you'll get things leaching into the water and other contaminants. So you're doing the opposite. Instead of cleaning, you're contaminating.
Did you report the surface area normalized absorption density? And if so, were the trends different or similar to the regular absorption density?
Not sure about this one.
I think if you looked at how much it absorbed per square meter of adsorbent, I believe.
Since there weren't many differences between the surface areas, I didn't look into that. Maybe that's something interesting.
And then Fred was asking, did you measure the acidity and number of sites on your chars? Mainly Lewis and Bronsted acidity. Yeah,
so you can do Boehm titration to figure out the acid sites and things, but I did not do those analysis. So I relied on the ultimate analysis, proximate and infrared mainly, and the pH.
Then a more general one, does it make a business sense to make activated carbon with biochar? Can biochar compete on performance and cost with conventional activated carbon for performance? So what's your opinion on that?
Very interesting, yes. I think it's worth to look at replacing activated carbon, or at least making the process more sustainable and economically efficient for everyone. So we're doing activated carbon from lower cost feedstocks, waste feedstocks, agricultural wastes, and I think it can achieve as good as performances as normal activated carbon. That's why there's so much research on it now, I think.
And then another question from Soliver. You presented the elemental makeup of the chars. Do you happen to also have the OC and HC ratios available to see how absorption correlated with this?
Indeed, it would be more straightforward to compare these ratios with the absorptions. But here I just presented the proportions of each element. But I do have those ratios. Definitely worth to look at if there's some correlations between those. Thanks for the question.
And then a question from Rob. Does this point to the need to pay more attention to designer char, research to improve the functionality of specific products for specific uses. So
Yeah.
about engineering biochar.
Definitely, the process is so dependent on feedstock and the conditions and the reactor you use that if you need so much research on this to functionalize. There's so many options as well. That's why you need to be really careful about when you're doing, say, trying to develop a commercial product. So you need to be sure that you get the right feedstock and the right conditions for the final application you want.